I think the department would like them really to be, and the problem for anybody who runs a small business, it's like, well, even if you're not making anything, it's sort of odd just to sit around at home too. So, and I think by building up goodwill, it really helps. Because I don't know what their arrangement is with the department, but there's got to be some sort of arrangement for them to stay alive. All right. Well, there are people out there. Hey, if one of you people out there can hear me, can you just write a quick response in the Q&A on Piazza? Thanks. All right. Does it sound like the speakers are on? Can you tell? Can you tell if the speakers are on? Okay. Yeah, well, they're not supposed to be real loud because this thing says it's on. Because the mix is really bad otherwise. If you can't understand me, let me know. Yep, yeah, it's working. Cool, thank you. All right, so today I want to talk more about the digital synthesizer history, introduce some ideas in digital synthesizers. There were a gazillion of them, so to talk about all of them is difficult. I'm going to talk about a few of them, and just like I did about analog, and more importantly, though, just ideas that came up and try to point out some things about that these things did that are still important today. A lot of these ideas that seemed sort of out of date for a while come back again. For instance, a lot of things that were done with discrete hardware now sort of have a counterpart in gate arrays and FPGAs and that sort of things. So there's actually sort of reason to look at some of these things, and some of them are just sort of historically interesting and referenced in various pieces of music, like we had the recent Blade Runner and such. The original used the Dartmouth synthesizer heavily. So what about this here? This Dartmouth synthesizer is also interesting because it's by a student project at universities. Originally started in 1974. One student was doing the processor, sort of a control processor, and another student was doing the sound engine. And that was a common setup. It's used now all the time in video, right? You have a GPU that is there to do GPU computations, and the program sets up efficient data structures for the GPU to chew through and do real-time stuff. Unfortunately, audio doesn't have a front row anymore. So, for audio, usually you just play recordings and maybe filter them a little bit. But maybe that'll change in the future. We'll see. In any case, in this case, this was a student project, started in 1974. Later, the company became known as Synclavier and sold for many years. One of the really important things that they had in there was sort of an odd thing to have at the time, was spectral analysis. And then there's also this idea of analysis synthesis. What does that mean? Well, it had enough memory that it could show you time-varying, short-time Fourier transform, basically, a spectral graph like you did in the first homework one. Those kinds of graphs, or spectrograms, of real sounds. And that was somewhat connected to the synthesis. I mean, it could play those back, but the core of the synthesizer was actually FM and wavetables. So it was sort of this mix of things, that they could do. And so wavetable synthesis, that just means a phase oscillator with a table lookup, with wavetables like we talked about. So the spectral analysis turned out to be super, super important because this thing was so expensive that very few people could buy it. Now, the U of I, had a well-to-do studio. It was quite famous already at that time. And so universities would have it, and a few very wealthy studios would have it. But it didn't have real wide distribution, but speaker manufacturers discovered this thing. And very soon, every speaker manufacturer had to have one. And the reason is that if you have, say you make microphones and speakers, well, you want to take real sounds, look at their spectrum, and then put them through a speaker and back through a microphone and see how they change. And then try different microphones, try different speakers and combinations, and try to figure out which of your components is doing what to the sound. To this day, we still use, if you buy a speaker, it has this ridiculous frequency response graph on it, which, if you think about it, is really asinine measurement of a speaker. I mean, I guess if it were really bad, you'd have to worry. But, it doesn't that's not very important for a speaker. I mean, then, yeah, it's something. But nobody listens to single sine wave. The graph tells you nothing about if you play two sine waves into it. Because, does the speaker break up when you have highs and lows at the same time? Does it, there's all sorts of issues about speakers that are really important that are not at all, a single sine wave is just, well, it's an engineer's test, and, it's something. Like I say, if your single sine wave has a really bad response, probably they're not good speakers. But so what they did here is every speaker manufacturer bought one of these. They never used the keyboards and all that other fancy stuff on it. They only used it to really improve their own products. And while that isn't really a musical thing directly, or at least not electronic music, it was super important for keeping the company alive and solvent for a long time. Because it's hard. You make this thing that's so expensive, and you try to sell it to people that don't have very much money. It's a difficult business. Anyway, it's quite a momentous thing that they made that. The first movie to have using all digital synthesizer. Use this synthesizer is Vangelis's score for Chariots of Fire, which many people know. It gets referenced a lot. If you've never seen it, it's something to watch and just listen. Okay, so that's the first all-digital synthesizer. Then we'll talk about microcoded synthesis. So this is related to the first. This also had a language that you could program in. But this is the Samson box, which was at Stanford. It was not actually built at Stanford, but it was built for Stanford. And it lasted a long time. I mean, this is, the foremost electronic music research place in North America, and they used the same thing from the 1977 all the way up to the 1990s. So what is it really? It's really sort of a sound computation accelerator, if you want to think of it like that. It had mixture of precompiled and real-time control, so you could play up to 256 very simple voices, or you could combine them together, components together to make more complicated voices. Most people didn't use this 256 very simple voices. If you did that, you had to have triangle waves and, various other limitations. So, but you could do quite a few things with them. It had no real-time keyboard. You couldn't play music on it real-time. Everything had to be pre-compiled, but it synthesized in real-time in the sense that it computed right away. And nowadays that sounds kind of, well, so what? But it's really big difference between hearing something computed quickly. The compile process wasn't very long, and then you could hear your piece of music right away. That feedback loop is incredibly important. Here at the U of I, when I was a student, a lot of people used music and languages to make samples, but it was a multi-day process each time you did that. And so if you want to tweak your sound just a little bit, well, 2 days later you get to hear what it sounded like. Very, very slow feedback loop there. And so it's nice to have faster computation. All right. So that's microcoded synthesis. I'm going to talk about a microcoded synthesizer after this next one that I built here as an undergraduate. It was a semester project, and then it took another semester, and then I did a master's degree on it. And then I did a better version, which I'll talk about later, for a PhD. So, or as part of my PhD work. So it was a bigger project than I suspected. It's a good synthesizer. But it wasn't. I'm not claiming it was the best in all ways of the time or something. One of the reasons I want to talk about it is just I know all the details about it, and it's good to see all the components that are important in these designs. Because those ideas are still around today. But before we go on to that, we'll talk about Australia here. The first digital sampling synthesizer was a Fairlight computer music instrument, and this was early, and memory was expensive still. So this was, the minimum memory you could get with it was about $28,000, and it was triple that if you wanted anything that we would now consider a reasonable amount of memory. So it was $28,000 in 1980s dollars. It was interesting because to pitch shift samples, it just changed the sample rate. So each voice had its own D-to-A converter and its own memory access mechanisms, and it would just run at different hardware rates. Because it's actually not very easy to change sample rate. And we have oversampling filters. We have all these fancy things now that are just built into your D-to-A. But, that was very, very difficult then. So it was, there's this deal of the cost of memory versus cost of processing power. Nowadays, memory is cheap enough that you would never duplicate a whole bunch of processors just to make better use of your memory. But at that time, that was definitely worth it. So there are a lot of different trade-offs. Okay, so I want to talk about this ROM microcoded synthesizer that barely fits. Yes. This was my work. I actually did the synthesizer hardware, and Kurt Hebel did the it's an 8-bit microprocessor, Intel 8080, the control processor for it. So again, it was this paired thing. This is like what nowadays would be a GPU, and the Intel 8080, which was only 8 bits and didn't have a multiply instruction, so it was a limited thing. But in any case, that was sort of like the main processor. And so what do you have here? One of the big things that just totally differentiates this stuff from analog modulars is multiplexed hardware. So the Cold War was on, which meant, didn't have a huge impact on music, I don't think, except that maybe Theremin was doing Cold War devices rather than cool musical instruments. But in any case, what we did have is multiplier accumulators. So this structure here is duplicated 16 times. So what happens is we have a ROM microcode that implements this, it's just coding that implements a code version of what you see here, and then that ROM microcode loops 16 times. Yeah. Go away. So that loops 16 times. So there's one ROM microcode that loops 16 times here, and it's all implemented using one multiplier accumulator. So these were multiplier accumulators that were ostensibly meant for code breaking and stuff, and fighting them evil Russians in some way. I don't know what. But anyway, they existed, and there were 64-pin chips, so, with 10th pin spacing, so they're nice big things. They use about 8 watts of power, so you could cook your breakfast on them. But anyway, we had one of those. And that actually made it feasible to build a synthesizer with it that didn't cost insane amounts of money. Yes, this one chip was the vast majority of the cost. So this one chip did only one operation, multiply and add. And you can see here, if you look around in here, it was used here once, twice, the same chip, and then 3 times, 4 times, 5 times, 6 times. So there are 6 places, 6 times that the multiplier accumulator was used. So this is one chip used 6 times. Well, that's not amazing, right? In hardware, digital, that's no problem. The analog counterpart would be a lot of wires. So there's 16 of these. Multiplier accumulator is used 16 times. Then there's routing bits, and this is really important. It's doing the structure, but the structure is sharing memory with a control processor, which by today's standards is incredibly stupid. Your toaster is smarter than that 8-bit processor was. But that 8-bit processor could write into these registers. They happen to be 12-bit registers. It could write into these registers, and it also had routing bits. So the output from this synthesizer, from each voice on the synthesizer, could either go to the output you hear, or it could overwrite some other register in the synthesizer and some other voice. So you could do modulation and stuff that way. So I'll talk a little bit about what this thing had in it. One of the things that it had slope generators. So at the very bottom here, if we just look at the bottom, there's a left output and right output. It was stereo. And this left output here is this multiplier accumulator. What is the multiplier accumulator here doing? It's just adding, we call the right increment shift, I think. I can't remember what these things were. It's just doing an add. It's just adding in a slope value. Thing is, all we got is a multiplier accumulator. So every number you want to add, it has to be a result of a multiply. So, hey, you take something where only one bit is set in this right increment shift, and the right increment. Anyway, this is a slope generator for your amplitudes. That is very important because the control processor was slow, and it could only get around to updating registers every 10 milliseconds. You need your amplitudes updated every sample interval. Otherwise, you start getting zipper noise, at least in some situations. And that's a really important thing to remember now, too, because in FPGAs or something, or whatever system you have, it's easy to think, oh, I'll update my amplitudes once a millisecond or something. Well, you'll get 1,000 hertz noise. And it might not be exactly, it might not sound like 1,000 hertz depending on what your update rate is, whatever else is going on. It could sound many different ways. It could sound much lower frequency if your update has some irregular pattern to it. It could be all sorts of things. So that kind of update noise or zipper noise, you don't want that. So it's also something you can think of as aliasing. There's a lot of different ways to think of that, but you really want slope generators. So that's what these things are. If you look at the core of this thing, though, each voice here is just a phase oscillator with extra bells and whistles. Here's this phase integrator, right? Like you see, there's phase register, and it adds in more stuff. And what is it adding in? Well, two different frequency values. Each of those are results of multipliers. The reason there's two of them is just so you can do frequency modulation on top of some frequency like from the processor. It was just a way to get more inputs. So this is a phase integrator, and over here it uses the top 8 bits. You'll notice these numbers aren't very big. Like in the phase oscillator thing, I told you, hey, this value here has to be 24 bits. That's true. In this case, so these 24-bit numbers are actually made by 12 by 12-bit multiply, which is a bit iffy. It's kind of like having a 12-bit floating point mantissa and a whatever it is, 3.5-bit exponent. Okay. But the worst is down here, the top 8 bits going into an 8-bit wavetable. Yeah. This is 8-bit synthesis. It's still pretty good 8-bit synthesis for what you can do with it, but it's that's the way it goes. This wavetable again was in memory. And there were routing bits for everything, like which wavetable of the memory do you use, where do the outputs go, and that kind of thing. But that's sort of that setup. So this idea of a microprocessor shared memory control is still a modern idea. The multiply accumulate operation in itself, yes, that was a Cold War thing, but in fact, that's how you tell a DSP from a not DSP. One of the basic things is if it doesn't even have multiply accumulate, it's certainly not a DSP, some general purpose computer. And a DSP, it doesn't even matter if it's only for audio or if it's a generic DSP, like a lot of TI DSPs are sort of meant for everything. They try to do a one-size-fits-all. Yeah, it's going to have multiply accumulate. So that's a really common thing. I'm going to play you a sound example here, which is Bill Schaefer wrote this. This was recorded in 1981. You see the date on here is 1981. So it was a previous synthesizer by Sherwin Gooch, which he actually developed a piece on, and then it was recorded off of this, but he didn't use all the features. So you don't hear any modulation in it or anything, but you do hear other things. One thing you'll notice in here, there's no random number generator. So it's kind of hard to make noise, and you can listen to it. There's something cute about things like this. In any case, the amazing thing is this one, the first international synthesizer competition, which was done by which Roland did. Tomita was the judge there, and he's like a super famous guy. He did amazing things on analog synthesizers. So you wonder, why would he award this thing? That some students at U of I did. Well, you got to remember there were no MIDI sequencers at this time. So just hearing fast sequences of notes and notes that were in tune and, all these fundamental things were really pretty new. Anyway, here's this thing. It's called Bigfoot, and then in parentheses, The Return of, by Bill Schaefer. some 60 hertz noise in there too. This window is behind something somewhere. Okay. Anyway, you get the idea. This stuff is available on YouTube if you'd like to hear the whole thing. Like I always do, I rudely cut things off. Otherwise, I can't talk enough. The other things you can hear in there, sometimes there's like these weird timing problems. Well, this was before Midi. And so what we had is we had a 1200 baud connection to the Plato system, which was sort of the forerunner of modern computers. It had flat screens, instead of the big vacuum tubes that you're used to when you were a little kid still. All this stuff was invented here, but at that time, 1200 baud was fast. In fact, when we showed this stuff, people would complain, like, why would you waste all that bandwidth? You can't even read that fast because, well, text was being put up. And now, if you have internet service that isn't fast, all sorts of things might be required, but yeah, we weren't downloading pictures on Plato. In any case, it was all had to be encoded very efficiently. There's a special 6-bit code that we used instead of the MIDI 8 bits in order to get this to go, and there was some time stamping and stuff. But 1200 baud, was amazing for communications. Remember, MIDI when it came out, and it still is over 31 kilobaud. So it's almost 30 times faster. And so it was a challenge to get all this stuff going. And I think, I think Kamita sort of realized what went into it and stuff. And it had a different sound to it than other things did at the time. All right. So, I want to talk about real-time FM performance synthesizer. This is very different again because in this thing, what Yamaha did with the FM, which was patented by at Stanford by Chowning, and even before that patent had already been used in music at least a little bit, but they went way farther than John Chowning did at Stanford, making this a real performance synthesizer. And that's very different than like what you just heard. What you just heard was actually patterns put in a music compiler. We had a keyboard you could play too, but that piece of music was done very differently. So a real-time performance synthesizer is really a different animal, especially when you do it on a grand scale, right? We must have built maybe 20 or 30 of those synthesizers total. A few other universities got them and that sort of thing. Well, this Yamaha DX7 had outsold all other synthesizers and organs combined. Like, that's big for several years. So why was it such a huge success? Well, I want to say some terminology first. FM operator, still a term we use. All that really is in our terminology that we've used so far is a phase oscillator that has a sine table. There's a table lookup and it's a sine. So that's all an FM operator is. So multi-operator FM was something that they really developed. Really, Yamaha engineers deserve credit for that. So you could have, instead of just having one modulator and one carrier, as you heard in that example I put last time, and as we're in the what at least until that time was the main thing that John Chowning had worked with. They made modulators on modulators on a carrier, or one modulator, multiple carriers, or multiple modulators, one carrier, all these different combinations, all these combinations that they sound useful. But they were predetermined algorithms. The advantage of having predetermined algorithms is you can make all your knobs actually do something useful. And that synthesizer you just heard, if you just random patched in there, you just get junk. It wouldn't even work. Your routing bits, it just wouldn't mean anything. You'd be lucky if you heard anything. And if you did hear something, it'd be very unlikely to relate to anything that you expected. And that's different here. Like here, you could twist knobs in any position and get a reasonable sound out of it. Or at least get something out of it. Maybe by today's standard, it wasn't as easy as a lot of digital systems are now that tout no learning curve and such. But still, it was well done compared to other things out there. There were predetermined algorithms, and that's very different than the next thing I'm going to tell you, which is this RAM microcode, where you're going to play, as I say here, synthesis algorithms not envisioned by the sound designer. The FM wasn't like that. This Yamaha was specifically, they thought through all the different options. They tried to make it so the bank of knobs really would do something useful in almost any situation. And people really learned. I mean, they came up with their own words and their own ideas of what these knobs controlled. Some of them were kind of weird because they're controlling some modulation of something or other. Yamaha was also careful to scale and offset the knob values so that you would have, you would stay within sweet spots. You wouldn't always just have a junk sound and not be able to figure out what combination of knobs could actually get you something useful. They really put a lot of work into that. So, why is FM so popular? Well, the main thing is you can change the modulation, the timbre, in real time under envelope control, and that's huge. You can, any time you can control how a sound changes over time. In the original Moog modular, right, the famous Moog brass sound was a matter of controlling low pass filter along with the amplitude of the sound. And similarly, with FM, it wasn't the same kinds of controls. It was different stuff, but you could do all sorts of things. And because they had all these different multi-operator setups, there's a lot of things you could do. You had 16 simultaneous voices if they all had the same uniform patch, if there are no splits or nothing. You had velocity and aftertouch. So this is something that most keyboards have lost now because people don't want to learn how to play with aftertouch. It's different than playing, if it matters what you're doing with the key after you have it pressed down, you go to the store, right? You try each keyboard for 30 seconds or however long it takes you to think you know it, and then you pick the one you sound the best on. And so if the keyboard does too many sensitive, weird things that no other keyboard does, So aftertouch exists only in a very limited state nowadays. Going to try to change that in the next few years, but we'll see. So they had velocity and aftertouch, pressure-controlled keyboard, and a good human interface. And okay, so a DX7 player told me, actually, it was really pain to use that. Okay, compared to other things of the time. Compared to stuff that people like me made. It had a really good user interface that was very controllable. And it also did all this keyboard scaling. To allow variation of amplitude and with pitch. We'll talk about FM later, but FM has real problems with aliasing. And you can hide those if you have the right kind of scaling functions. Again, something that's very difficult for a musician to always have to set up themselves, but if they have some prefab stuff to help them with it, it just solves one of the underlying problems of FM right away. And they did a good job of doing that. All right. Any questions about that? In a non-COVID year, I usually have a couple of people who own one of these or own a similar thing, and yeah, it's still a big thing. Although, FM synthesizers have improved dramatically over time, and people have done all sorts of stuff with FM. Okay, so this next thing here, see if I can get most of it on there. Like that. There we go. Okay, so I'm going to talk about the synthesizer with RAM microcode. This was just an evolution of what I worked on with Kurt Hebel, who was one of the founding members then of Symbolic Sound. In fact, Carlos Scaletti and Kurt Hebel founded Symbolic Sound. Carlos Scaletti had this music language that she had thought of Kima, and this was the first platform it was implemented on. It wasn't what it was made for, but with some extensions to the hardware that Kurt Hebel came up with, it was possible to implement it. So, what is this RAM microcode? Well, RAM just means you have a lot more programmability. If you have routing bits or knobs you can twist, that's nice, but RAM microcode means that you can program anything. It's just, in some sense, a somewhat generic computer. This had a horizontal microcode. That idea is still very important. This thing had a 48-bit wide microcode, and what did all those 48 bits do? Well, they controlled all the individual control pins on all the chips. Like there's three. This is sort of a hardware diagram now. This is different than the previous diagram, which showed what did the software implement. This is just, there were 3 multiplier accumulators, and it had all the control bits of those. It had 1,024 registers, which was huge then, and even now most, a lot of processors don't have that many registers. Most of them have like 16 or 32 or 48 or something. But it had a bunch of registers. It had a huge RAM memory. This was slow access, though. It was dynamic RAM, so you would write an address to it. It's kind of like accessing disk nowadays. You write an address to it, and then 6 instructions later, you could get the data. At the time, this was considered very fast memory, and 1 meg by 16 bits was huge, maybe not by today's standards. There was an I.O. to a Macintosh control computer. Started out off as a 68,000, but when Mac came out, they used the same 68,000. It was just cheaper to get a Mac and cut open and connect to it. It's a closed system normally, but you can always open up a closed system, solder to the board, and connect your synthesizer that way. And then there was other stuff not shown here is how the program memory worked and the address bus and the program bus. But anyway, you sort of get the idea. Very little here. Right? Some very fast RAM, 3 multiplier accumulators, and some FIFO queues, which we'll talk about in a second. So we have 3 multiplier accumulators. Why would you have that? The modern counterpart to that kind of idea is a SIMD machine, single instruction, multiple data. This isn't even quite that. This is yet a different turn on because there's sort of it's almost more like single data, multiple instruction. It's sort of a different thing. But anyway, it turns out that in a lot of operations, say just think of a FFT. If you wanted to optimize an FFT for this kind of structure, it turns out in FFT, the same piece of data is multiplied by many different things. And if you can optimize your bus bandwidth so that you load inputs to your multipliers whenever the data is available, and then do the multiply whenever the other, basically you can do an enormous amount of optimization this way by having 3 multiplier accumulators at once. A common example for using 2 is just for stereo computations, right? You have a left channel and a right channel. In any case, we had 3 multiplier accumulators, so this was a more expensive thing. The horizontal microcode, the main thing about that is that there's no decode time because, computers were getting faster, but even just problems of light delay. Remember, these are pretty big chips and stuff, and, electricity only moves about a nanosecond a foot. So if you have a board, if you have too big a board or too many wires going lots of different places, you lose a lot of time. So you lose a lot of speed on your processor. So having horizontal microcode where there's very little decoding is good to get. This was in the backdrop of mostly at that time Processors like to have 8-bit instructions, not 48-bit instructions. And why is that? Well, to save memory. Memory is expensive. But, then somebody had to already have an idea ahead of time what instructions you're going to use and how they decode. So anyway, so this is a horizontal microcode. Still an idea now. My favorite modern architecture is analog devices. They call it super Harvard architecture. Harvard architecture has been used for and abused as a name for lots of things. But this ain't your pick. This is a really high performance thing. And again, they have 48-bit instruction words. Now, their thing does a lot more than this. It's not just a horizontal microcode. But still, it means you can do lots of things in parallel. And that's a big deal. Harvard architecture, what does that mean? It just means you have multiple memories, multiple buses. Often multiple, like in analog devices, you also have 2 ALUs, and 2 address generators. You have a lot of, just multiple stuff. It just means you can do more things in parallel. It's very different than von Neumann. Von Neumann's big contribution was, hey, really, the kind of memory you use can be the same for data and for instructions. And people didn't really realize that, so that was a cool breakthrough. On the other hand, if you keep separate buses for different datas, for different instructions, instructions, data, addresses, all that stuff separate, you get a lot more throughput. So there is still reason, even in modern times, to have a Harvard architecture, but kind of like GPU architecture, the number of people that really understand this kind of architecture are minimum. And so, so it's a real skill to program those things. Okay, what do I have here? Harvard architecture, parallel operations. Yes, because of the Harvard architecture, parallel buses and horizontal microcode gives you lots of parallel operations. FIFO-Q and multi-rate processing. Those are important things I want to talk about, sort of a separate topic from parallel and Harvard architecture. And that is, these FIFO-Qs are really important because they allow for multi-rate processing. What does that mean? In a previous microcode and a lot of different synthesis systems, if they didn't have FIFO-Qs, what that means is every sample computation better make it within the sample interval. Like say you're going at 50 kilohertz sample rate just to make it easy. That means every 20 microseconds you have to have a sample computed, no matter what. And that's really inefficient. You lose like an order of magnitude of computation power if you put that kind of requirement on a system. You're way, way, way better off doing this multi-rate thing. So what does that mean? That just means that whenever anything unusual happens, like, a new note starts, then you might have to do a lot of computation. And while you're doing that, you computed several samples ahead and put it in this queue, in this first in, first out queue. So you don't run out of things going to the D to A. Say you're 20 samples ahead, you have 20 sample intervals. You have 20 times 20 microseconds that you can spend on this note starting before you run out here and your system isn't working anymore. Does that make sense? So it's really important because it means that when a new note starts, you can do all this extra processing to pre-digest all the data so that your main sample generation loop, the loop that happens 99% of the time, is super efficient. It knows it has all the data exactly in the format it needs. Everything is set up for it so you can have a super efficient core loop. And let's say it can compute samples in 10 microseconds. Then you're in really good shape because you spend your 100 microseconds processing this new loop, note, getting everything. But so you have that sort of slow rate of processing, which happens whenever an event happens, or maybe it happens once a millisecond. But anyway, if you can do slow processing only every once in a while, and then and in return for that, do much faster processing elsewhere. And a common example would be filter coefficients. Say you have a filter and it has some cutoff frequency. If you can pre-compute those cutoff, those filter coefficients, because the cutoff frequency doesn't change very often, right? That's huge than trying to compute the filter coefficients every time. And, that idea extends to lots and lots of other ideas. So that's what this multi-rate thing is about. And that's why you want FIFO-Qs. And one of the things that is always said about Midi, about how slow it is and this, that, and the other thing, almost always those problems are in your computer because software in a computer has very long FIFO queues. Like really so long that they're almost unusable in real time. People still use it. People still use Ableton stuff, and they still have 10 millisecond delays through it, and they somehow, learn to deal with it. But a computer has to have really long FIFO queues because it's trying to do everything, What happens if, I don't know what, Adobe decides to do an update at the time you're trying to play your concert? All these different things happen, and it has to have a lot of queuing to guard against that. Because easily on a computer, you can be several milliseconds at a time where you don't get the CPU. Right? Another reason why a lot of people don't like computers on stage. And I got something in my eye. How do I get something in my eye when I'm wearing a mask? Okay. Any questions about that? Does that sort of make sense? So this multi-rate thing is really important. In the Egan matrix, you will see that too. Like formulas are evaluated every millisecond, which is much slower than the sample rate. And even the sample rate varies. Some things are evaluated at 72 kilohertz, some are evaluated at 36 kilohertz. They're all different rates, whatever I needed for this or that or the other thing. But there's all these multi-rate things going on there, and but then there's all this interpolation and stuff between those once a millisecond evaluations for formulas. And that's, yeah. So, yeah, that's also a very, very highly optimized system there. Any questions? How many people have heard of Harvard architecture just in some other context? Yeah, it doesn't really mean that much nowadays, except, multiple memories, multiple buses. So, like, you could access, 3 different memories at the same time in one instruction. Where von Neumann architecture, the cool thing is you have one big memory, and you don't need to split things up, right? So there's advantages either way. Similarly, most applications you really wouldn't want to write on a GPU, right? A GPU is really good for the specific thing it's doing. And that's similar for these Harvard architectures. I don't suggest you write Microsoft Word for it, but it's good for other things. Just to show some pictures. Pictures are always cool. Here is, we call this thing the Platypus. You can see back here. There is the boards with lots of chips on it. The vertical part is the DDA converters. This was before CD players came out. So the DDA converter was a super expensive thing. Easily $600 for a D to A. And then you had this analog filter that had to be a variable cutoff filter. It was just a big thing. Anyway, that's the vertical part there. The horizontal part is this thing. I can't see the multiplier accumulators. That must be on the other side of the board. I don't know. They're big honking things. This is these you normally see nowadays as fish tanks, but this is the original Macintosh. After they got their windowing ideas and stuff from their Xerox defectors, and in the back here you can kind of see that there's a cable to go into the box because we drilled holes into it because we wanted access to the processor. This was a really cool computer at the time. By today's standards, booting off a floppy disk takes patience, but hey, it was really cool back then. Yeah. I don't know what this has to do with anything. That's Bob Moog at a 1988 at the International Computer Music Conference here at the Music Building. He is always a nice guy. He was always very supportive and wrote nice articles about what we did and that sort of thing. Cool guy. All right. So I want to just make a comment about MIDI keyboards. We're going to do much more about MIDI in Lecture 7 and 8. So what does MIDI stand for? Musical Instrument Digital Interface. So mid-'80s, this came out. It was done by a consortium of synthesizer makers. And what is so important about MIDI? Well, these are really fundamental things. They're really, really important. Hook any synthesizer to any keyboard. And while that seems not that amazing now, right, at the time, people had to build a keyboard and a synthesizer, both. And that's huge. I mean, you might be really good at synthesizers, but not so good at keyboards. Or you might want to make a really nice synthesizer, but if you also make a really nice keyboard to go with it, the whole thing just costs a lot. And by being able to mix and match with MIDI, that's huge. In addition to that, you could talk to computers, so you could do your timbre editing on computers. Your tiny little display, which is sort of hard to menu dive with. And that display, 3 years from now isn't even going to be made anymore, so your hardware's out of date right away and that kind of thing. Hey, if you can talk and do software on a computer, you can take advantage of a beautiful high-resolution display like that thing, which is 512 by 512, same as Plato was here in the 70s. You could do all sorts of things with it, and that's kind of cool. And you can do sequencers, like that thing you heard before where you have patterns and where you have a music compiler and stuff, or a digital audio workstation. You could do all sorts of fancy stuff, right? And so it's huge. It's easy to complain about MIDI, but it's huge. Okay, I want to play a short sound example here. This is Laurie Spiegel. It's called Cavus Murus from 1986. Cavus Murus, I can't pronounce anything in Latin, but it just means mouse cave. She was in some studio. A lot of studios would use old curtains from wherever they got them from because they make great sound dampening. Problem is, the places that threw out their old curtains threw them out for a reason. And so when you inherit these things, you may have inherited a lot of rodents and a lot of other things. But in any case, this is a piece of music where she's interactively playing with her mouse, the different kind of mouse, with the mouse on the computer, and playing this composition. So it's sort of a computer-aided composition, but with real-time input and control. Laurie Spiegel and many other things. She, if she ever comes by again to do performance here, as she does every N years, not to be missed. They're always very entertaining. So here is Cavus Murus. And this is on a Macintosh, same as that thing there. What else can I say about it? I'll just go ahead and play it. So, yeah, this is homegrown C code, and it's a rack mount version. It's Yamaha TX81Z, which is a later rack mount version of an FM synthesizer. But all those sounds are FM sounds, and, clearly very different than the two-operator FM that you heard last time, right? So you can make many, many different sounds with FM. All right. That's Laurie Spiegel. What next? We have MIDI control of analog synthesizers. And there is a long list of failures here. And it's continuing today, and this is, very much my own opinion, but almost always when you can save patches on an analog synthesizer, even very good analog synthesizers, which I won't give by name, when you save patches digitally in memory and recall them, you get something really close but not exactly back, which is, pretty bad, right? There's a few analog synthesizers that are in the $40,000, $50,000 range that have been built that don't have this problem, but that's just crazy, right? Because if you're at all, if you're extremely picky about what you're doing and you've got the perfect thing, saving it then getting back something kind of like it is like a real slap in the face, right? It's not very useful. So in the analog world, when you have an analog setup, if you really like something, you commit. You record your track with it, and then you go on. And that's part of it, and that's even part of the music, what it sounds like. It's part of the compositional process and part of the recording process. And this attempt to save things digitally, and similarly to control things digitally, it's just, so I have some here, analog strength, the immediacy. That immediacy just means you twist a knob and it's directly just controlling the sound. It's not going through any OS. It's not going through a message pump, or it's not going through any FIFO cues. It's not doing any of that. It's just controlling your sound. So there is a real immediacy there. Sometimes people imagine things, and sometimes they don't. Sometimes they imagine things like, analog synthesizers have no delay. Well, it depends what you're thinking about, but certainly filters have a delay through them, right? Nothing happens instantaneously. So that may or may not be a valid thing to say. But there's no sample rate, certainly, to worry about. You don't care if you alias, doesn't matter. And in some rare cases, you might even have sounds that in the end, the stuff above the half sample rate you can't hear anyway, whatever that frequency would be. But you could have an algorithm that is an intermediate stage, makes something above a half sample rate that then later, because of some nonlinear operation, gets shifted back down to something you can hear. So there's all sorts of things about sample rate that are problematic. So there's no sample rate. That's cool. There's this detail control. What does that mean? Well, if you have a modular, you can get into the guts of your synthesizer in lots and lots of ways. But in digital synthesizers, even from the very beginning, like if you had that Yamaha synthesizer, those knobs are pre-digested for you. And that's useful if you just want to twist them and get different timbres and, listen to what you're hearing. But if you want to, you don't have the option of getting in there and just changing completely what that knob does. Where if you have an analog modular, right, you can patch things differently. And so there's a lot of different things there. The Egan Matrix is sort of a weird digital synthesizer, right? Because it tries to mix some of these things. You can go in the Egan Matrix and change things, but it's it is a unusual digital synthesizer in that way. So the digital strengths, the big ones are repeatability and multiplexing, right? Once you have something, tomorrow you can come in and get exactly the same thing again. When you try to do that for an analog system, things heat up at different rates. All sorts of things happen. Your oscillators drift, everything drifts. And you won't have exactly the same thing. That's part of the charm, too. It's not at all just bad. But then there's the multiplexing is important because you can play multi-voice things really easy. You don't have to patch the exact same thing n times and then hope they sound similar enough to be usable. All right? So most are failures. There are some successes, really important successes. People have figured out a lot of stuff. The first one I talk about is a much more recent one, one of my favorites in this class, and that's you take an analog modular synthesizer and you make a module for it that has analog in, analog out, but it's actually digital on the inside. Now, there's, a lot of iffy results there. There's also results that sound really nasty, but hey, sometimes nasty is what you want. So that's all okay. I'm not putting that down. But there's also things that really fit in amazingly well just because of incredible skill of the maker. One, I think his name is Tom. I'm sort of, but the Herb Verb is made by an East Coast company by Make Noise, but the designer of it is at a West Coast university. He's a professor at. I shouldn't say. I always get things wrong. But anyway, the Herb Verb is just an incredibly cool thing. And, yeah. So that's a digital module in an analog synthesizer. Or later in the course, we'll talk a little bit about some reverb, not a lot, too many things in this course, but we'll talk about it some. And he did a really clever, granular implementation of a classic reverb algorithm, the same reverb algorithm that I copied for and modified for the Egan matrix. Yeah. Okay, so I'm going to play you another example here of digital controlling analog, which is much closer to home. And let me see if I can bring this up here. Yeah. Okay. Okay, so this is the Moog Voyager. Now, the Moog Voyager is not a modular synthesizer in the sense it doesn't have lots of patch cables. It has a standard analog chain, as they call it, a standard sequence of things, and a bunch of knobs to control it. And it has a keyboard built in, it has bend wheels, the usual sort of setup. But it has, on the back, it has some analog inputs. So it's not an analog modular in the sense that you don't have lots of different modules, but it's a pretty amazing synthesizer because since the 60s, it's been under continuous development and improvement over time. And so you can control it through Midi, but my preferred way of controlling it after experimenting with things is through there's analog connections on the back. So what you're going to hear here is a continuum, and then our own voltage converter to get analog control voltages, and that's connected back here. There's some in-between processing here, which at the time, because we didn't have this built into the Egan matrix, at the time this was patched in a different analog modular. Now, if you're really into this, if we do have final projects and you want to do something analog, I could bring in a converter, and this kind of patching or pre-processing can be done inside the Egan matrix. There's a module for that called the CVC module that you can use with that. Anyway, so this is played on a continuum. Now, a continuum is, people always think it's an analog thing, but it isn't. It's all digital in there. It has Hall effect sensors, and those go through an analog multiplexer tree, and that then gets A to D converted. And from there on, everything's digital. So, the fact that it's continuous doesn't mean anything. It's also all MIDI inside. It converts everything to MIDI. People always think, oh, MIDI is, can't do continuous. I don't know. This certainly does. So the part of the software that does the Egan matrix communicates with the part that tracks your fingers through MIDI, internally and also, of course, externally. So anyway, so I'm going to play you this example here. This is a Moog Voyager controlled by a continuum. So continuum is a digital controller controlling the Voyager, and it works out very nicely. In fact, the nice thing about a Voyager for us was, it's, as I'd mentioned before, it's hard to sell something expensive to people that don't have lots of money. But people that already own a Voyager have invested a lot. Usually they'll have, over their lifetime, already spent $20,000, $30,000 in the studio, and at that time a continuum was like $3,000. It was a worthwhile extra expenditure. And you got sounds out of the same analog synthesizer, which is quite a beautiful synthesizer. Got the same analog synthesizer, and people got sounds out of it they'd never heard before. So I'm going to play here. This is called Voyager ANC. I can't even remember what ANC is. But you hear there is a digital modeled piano, but everything else is the Voyager that you're hearing. So this is played on a continuum, controlling a Voyager, but no Egan matrix sounds. So that's digitally modeled piano. So that's digital control of analog, and it can really work. You know, one of the things you want to do in your digital is be really careful about how continuous it is. And really how you encode things really matters. And people are often very, very sloppy about it. Also, MIDI rate is, you know, a fairly low rate by today's standards. 31 kilohertz is not, or kilobaud is not very fast. But if you're very careful about what you encode, it's fast enough. And in this case, we did use an analog connection to it, partly because of the Voyager's MIDI implementation assumed other things in the continuum. For instance, it assumed you have a cheap bend wheel, so it just filters the bend too much. It assumes that you're controlling volume by a pedal or something, so it filters that too much. So there's some problems with the MIDI implementation, which isn't really that they did a bad job, it's just what do they assume is at the other end. So in this case, yeah, we used analog control of it, but it's all it's digital. It's all digital here. It turns to analog in an analog converter. All right. Any questions about this stuff? Yeah, there's a kind of nice cello-like sound in there and stuff, and that's, you know, it's a sawtooth, right? But if you play the right idioms and you play and continue your shape, well, if you, I couldn't do it, but if you are skilled enough to play it, it can sound quite beautiful and quite with quite simple things. All right, so what about analog synthesizers? Well, analog synthesizers are still really popular, despite all the problems with them and all the things. Why is that? Well, in the 1990s, Dieter Dupfa, like his name sounds like, a good German name, he came up with this thing that's now called Eurorack, which is these small little miniature connectors, small little miniature stuff, just to make modulars less expensive. Electronics have miniaturized, you know, using eighth-inch, what we call eighth-inch connectors. Of course, everybody realizes, right, there's never been an eighth-inch connector. It was smaller than quarter-inch, so people said, oh, it's eighth-inch. But there's nothing about it that's eighth-inch. It's just a silly name. But anyway, the eighth-inch connectors, or 3.5 millimeter connectors were much less expensive, and everything was scaled down so that the rack didn't take so much space, so you could carry it easier, all sorts of things. He standardized how power was distributed. You know, nothing super fancy about it, just sort of standardized, made it small and made it inexpensive. And if you buy Eurorack modules now, they vary anywhere from, you know, $100 to $600. So it's not that cheap, but a lot more if you had the big robust hardware. So why do people like this? Well, one of the things is it's craft hardware. It's not mega corporations. You know, one of the things about digital is once you get it figured out, it's hard to get it figured out. Once you get it figured out, you can mass produce it. Well, people like, you know, small manufacturers. People like the sound of, you know, just the feeling, oh, somebody in Oklahoma in, you know, some small town made this thing, and it has its own sound. And so people like, you know, buying that, putting it in the rack, and they're willing to support some individual that's sort of identifiable. You can get inside the sound, not like a sampler. Yeah, I mean, again, it's a modular. And the physical feel of knobs and fine adjustments. Now, some people are very particular about what their knobs feel like and will only buy certain kinds of modulars from certain kinds of, you know, modules from certain kinds of companies because they really want the right feel of knobs. And many of those people will shy away from this. So this doesn't have all the, for lack of a better word, snob appeal. You know, and I don't want to just snob appeal. I mean, it's like keeping your piano clean or taking good care of your violin. Maybe snob appeal is the wrong word. But the main thing here is more of a, hey, anybody can get into this. Anybody who wants to save up a little bit of money can do this stuff. And so it's a market that's growing all the time. And it's very, very much alive, and very, very much alive with small manufacturers. In Illinois, once this COVID stuff is over. I think the single biggest conference of this kind is called NobCom in Chicago. In the good old days, it was in September. We'll see what happens. But there's many different conferences about it. Here's a cool thing. Now, this is not Eurorack. This is a different standard. In this case, it uses banana plugs. There are real advantages of banana plugs over other things, but they're also expensive. So it depends what you want. This is Edmund Egan, the same guy I made the Egan Matrix with, but I was very impressed by the stand. He made the stand because he wanted it to look cool, but also he invested a lot of money on this, and as a practical matter, all the patching cables and stuff sort of get in the way of each other, and for him, this design was a good design, and very memorable. All right. Looks good here. Do we have any questions about this stuff? Any comments? Otherwise, I want to talk about homework a little bit. Because this homework will be, for some people, for physics reasons, because you aren't into springs, which isn't supposed to be a difficult part of it. But this homework is something different, very, very different than the last homework. And for some students, very difficult. For people that are into algorithms, this is sort of more second nature, but it depends. So, this homework was about music engraving or music printing. There's going to be terminology here that is used in the business of music engraving, and even if you are, musically. Talk about music. Some of the words like casting off and neighborhoods and things like that may be new to you, but I'm going to talk some about this. So this part of the lecture here, I've got 12 minutes, is not intended to make it so you don't need to read the article. It's intended so that when you read the article, you at least have some start on what the heck is this. And again, if you're here and you want, afterwards you can also take pictures of what I got if I talk too fast or if you can't take notes on it. But let's talk about here, this will be question 2, and about line breaking. So what is a line? Well, a line is actually usually called a system in the business. But a line is, hey, there's one line of music, another line of music. This turns out to be really simple systems. It's not a grand staff. It's not an orchestra score or anything. It's just in single staff systems. Or single staff lines. But in music, you always justify your systems. And justify doesn't mean you stand up in court and say why it's this way. It means on the right and on the left, the columns are straight. It's kind of like in newspaper print, right? In newspaper print, the columns are always same width. And as you know, in newspapers, sometimes it looks really dumb. Like you'll have a word that's like way spread out because, they're trying, for whatever, either they were sloppy or they couldn't figure out how to do it better. A lot of times they just don't care. Newspapers, the idea is to get the information across more than to have every last page be a work of art. But in music, music is always justified. So when you're doing music engraving or music printing, making sheet music, you have to figure out where to do line breaks or where systems get cast off. So casting off means, hey, after bar 5, do I cast off, which means go to the next system, or do I do it at bar 6, or do I do it at bar 7? Okay, and in this music here, every bar has a number on it just so that we can talk about it easier. I know that's sort of a weird music printing thing, but other things about this music printing is good. This music doesn't have a lot of totally bizarro stuff in it. This music is, printed by a good algorithm. This was done at the Ohio State University. There's very few good articles about this. In fact, this was never even published. The article you're reading is something that you can write to Ohio State for and get a copy of, but, I think the professor was too weird, even though he did some of the best work I've ever seen in music printing. It was too weird and didn't get tenure. So, oh well. That's the way it goes in engineering. So anyway, so we got line breaking and casting off. So we got this. We have to decide how many bars, how many measures do we want to put on each system. And so what we get here is this graph here, which looks intimidating at first. It really isn't so bad once you figure out what it is. These are the possible line breaking locations in the graph. So it's built from top to bottom, but then it's read backwards from bottom to top to figure out what you actually want to do on the page. So how does this work? You start at bar 0, but just because you always got to start at the beginning. And what these lines are here is if you went to 6, as a final thing did, then it has a demerit score of 7. What does that mean? Well, just a second. If you went to 7, it has a demerit score of 588 or whatever that number is. My eyes are old. Okay, so and if you went to 4 or to 8, the other ones aren't even listed because they're so far off they're not going to be useful. So this graph only has the more useful options. So you have these demerits. What does the demerit mean? Well, if you were to print this music without caring how long it is, just to print it in the most beautiful fashion you can, which we'll call the ideal spacing of all the symbols, then it's going to have some length. And you can either, say you want to put 6 bars on there, you can either stretch it out some, or if the length was too long, you can squish it down some. And that's what the demerit has to do with. How much, we imagine a force in this paper, I'll talk about in the next page, how much force do you have to expose to stretch it out or squish it down to the proper size? All right? So that's it so far. So that's how the demerit works. So basically, very little force had to be used to make it this length. A lot more force was to go to 7. Now, you don't just automatically use or as you would call a greedy algorithm, where you immediately go with the least one, because you don't know what's going to happen later in the page. There might be some place later. I mean, you can think of all sorts of pieces of music. Well, like here, for instance, down here, you got all these 16th notes. And these quintuplets here and all this stuff. You know, this is a pretty long bar. And you have if this bar is going to appear somewhere, it's got to be on this line or on the next line. It's pretty quantized there. Where up here, you actually have a lot more choice. These bars are all shorter, and there'll be a lot less squishing or stretching involved, depending on what decision you make here. So you really want to make a graph like this where you say, okay, so now if we cast off at 6 as the final decision was made, but this is before the last, then we could go to 10 or to 11. And again, other options were just too far out. And so at 10, you have a demerit of 970. At 11, you have a demerit of 1. And it turns out it did pick 1. But that won't always happen. It won't always pick the lowest demerit. It'll usually pick it. And it's really important, that difference between always and usually. So anyway, so you go through here, and then for 7, the only reasonable next option was 12. And for 12, then the 17, and so on and so forth. And you can go through all of these. Some of them cross-connect again. If you went to 11, you could then also stop at 18. It turns out that wasn't chosen. 18 is like right in the middle of a line. But when you get all the way to the bottom, well, you got to get all the bars in. Right at the very bottom, you got to start. You got to go to 48. The composer will be really mad if you leave off the last bar because it didn't look pretty. So you got to go to bar 48. So here you're at bar 48, and now you can go backwards. There's only 2 paths that led here, and you just go through and you find the smallest demerit path all the way back, and then you're done. That's where you cast off, at those bars on that smallest demerit path. So this may not make immediate sense to you. I would be surprised if it did. The idea is that you spend 4 hours a week on homework. That includes typing your answers, but so I want you to think about it some. You can talk to other people if you got somebody to talk to in class. You can ask things on Piazza, but please spend a few hours at it on your own trying to figure this out, because algorithms like this, there is no magic pill. If you've ever taken an algorithms class, they're not always real popular because new things are always thrown at you. And so it's just good to kind of look through this. Why am I doing this? Well, partly it's good for you to see what goes into something like sheet music printing, which seems like, sheet music has been around a long time. It seems But also, these nobody ever really does anything. That's where the big changes happen. So don't just discount this. Well, I don't even like sheet music. Why would I do this? Don't do that. Okay, are there questions about this? And obviously this isn't going to make total sense right away, but this graph, again, you build it from top to bottom, and then at the very end, at bar 48, which is the end, you only got a couple paths there. Then you go backwards, back up again, and try to find and do find the least path. And that's not a very long operation. There's not that many choices going backwards. So you find every path that gets you from here back to the top, and you add up demerits. You have the demerit total for every path, and you take the one with the smallest demerits. All right? So that's the one idea. So there's another really important idea in this thing, and that is this graph here. Please start on this early if you are not that good at algorithms, or even, why not? I mean, you got to do it sometime. Might as well swallow the pill early, because then you can ask on Piazza during office hours or any other time if you are willing to wait longer. And you can also let it give time to sink in. At least for me, a lot of times these things, when you try to do everything in one all-nighter, it's not so good. If you give yourself more time, it's better. So I want to talk about this graph here. What is this graph? It's very important. This graph is almost always misunderstood. So don't misunderstand it. This graph shows for one set of notes, say from bar 0 to 6. It's not showing you, oh, well, if I do bar 0 to 7, what happens? Or bar 0 to 5, what happens? It's not showing you that. It's showing bar 0 to 6. Just as an example, or whatever. This is a generic graph example, but it's showing you some information here for one set of notes. It's not showing it for a different set of notes. The horizontal axis is distance stretched or distance compressed. So the origin here is, if you did the ideal spacing, if you just laid out the notes the way they would most ideally fit, now you got to justify them. And this graph tells you how much force, vertical axis is force, it takes to compress or extend them. So force is like demerits, like you don't want to have to extend a lot of energy, a lot of force. So what is going on here? Well, say you did bar 0 to 6, just for an example, and you have to stretch it out. And you have to stretch it out this amount. Or here, I better do somewhere where there isn't a dot, dot, dot. This amount here. Then you can see, oh, well, if I have to stretch it that amount, this is the amount of force I take. And you read it off the graph, and that's what you use it for. Or if you had to compress it down, you could say, hey, how much, if I had to compress it down this amount, then I could read here, this is how much compression force it takes. Okay, and you want your magnitude of your force to be as small as possible. There's some things to look at this graph. It's like, well, when you are compressing it, no matter how much force you do here, you can't compress it more than this point. Why is that? Well, because you get cymbal overlap, right? In music, you can't, there's a limit to how much you can compress it. I mean, if you just have a big blob of black ink, that's not useful. That's not readable music. So there's a limit to how much you can compress, and that's why this line is vertical here, because you can't compress any more than that. Then let's look at the positive side. Well, you can always stretch it out more and more and more, and in fact, cheap music is often printed with the notes really far apart, and it's a pain to read, and you got a lot of page turns on. It's not that useful. Sometimes the notes are really far apart because there's lyrics in there, and the words are long, and that's hard. That's a trade-off. There's all sorts of different variations on why you would space things, but in the stretching, you can always move notes farther apart. Musically, it still works. So the stretching here, you can always stretch it more and more, but eventually your force is getting high enough that why do it? Now there is a weird thing going on here Why is it that this function is piecewise linear? It goes from here to here, and then suddenly, if you apply a little more force, you actually get more stretch than you would before, right? The slope keeps going down, which means that for just a little more force, it gets a lot more longer than it did before, and more longer, until you finally get to this point where you have one last line here, which is straight. But why is it that it's piecewise linear? And that's really important to understand out of the paper. Well, first, you see it's piecewise linear. You see some things labeling on here. You can understand those labels later. But it is piecewise linear. And why is that? Why are there these breakpoints, as we call them, between the linear segments? Well, the model you want to use is like this here. I just kind of scribbled this. I've got 16th notes here that are all the same duration. So ideally, when you ideally space these notes, all 16th notes are the same distance apart. They're in the same neighborhood. Neighborhood just refers to this part of a piece. Sometimes other parts of the piece, if it changes tempo a lot or something changes about it, you'll have a new neighborhood and you'll have new spacing, ideal spacing rules. But for this purpose here, we're going to assume everything is the same neighborhood, and so all the 16th notes should have the same distance. But these two here are really far apart. Why is that? Because there's that bass clef there in between, and you don't want cymbal overlap. So even though they're the same duration, already in the ideal spacing, they're not equally spaced. Because even ideal spacing is just before justification, but you can't have cymbal overlap. And here, there's a little less stretch, although I didn't draw this too well, because there's an accidental there because of the sharp. So we have this idea of springs between the beat lines. These little things that look like resistors or squiggles or whatever they look like to you. They're supposed to be springs between the beat lines here. And the idea is that at rest, this spring is at rest. This spring is at rest. This spring here is at rest. This one's at rest. That one's at rest. That's ideal spacing. All these springs are at rest. Except for these two. These have to be pre-stretched because even in the ideal spacing, they're pre-stretched because you need the extra space for some cymbal. All right? So these are pre-stretched. This one's pre-stretched. Now, let's say you applied some... I went over. I'll try to make it quick here. Say you apply some force to stretch this out. Okay? Because that force is going to stretch this spring, all the ones that are at rest are going to stretch for that. But not this one. Because it's pre-stretched already. That force has to overcome this pre-stretch force. And that the force you apply also has to overcome this pre-stretch force. So what happens here with these breakpoints is that the first, in this simple example, the first thing that's going to be overcome is this sharp pre-stretch force. It's sharp. It's not pre-stretched that much. So as soon as you applied so much force that things are so far apart that you don't need any extra space for the sharp, because notes are already so far apart, the sharp easily fits. Then you get to one of these breakpoints. Because then you're stretching this spring as well as all the other springs that you were already stretching. And then as you stretch even more, then there'll be enough room for this cuff change. And again, this spring will be involved, and you get another breakpoint. So just to make sure you know, when you have a single spring, you got F equals Kx. If you've got two springs in a row, or each additional spring here for the sharp and for the, you get easier stretch every time you add a spring, because each spring does F equals Kx. And sorry I went over. Thank you very much. If anybody wants to take a photo of anything, go ahead. Or if you got it, that's good. About labs, next Wednesday is a no class day. If you have a lab on Wednesday, please arrange to do it some other day. Just write to all the TAs, spam us all. You can copy me on it too, but spam us all and figure out some other time you can come in. Very worst case, if you join another lab team and stand back and watch them or something, that's fine. But please make some sort of arrangement for Wednesday. Thank you.